Okay, now you also see my cursor. Great. So hello and welcome everyone, and thanks for staying around. So in this talk, I'll tell you something about what we did with together with Mark Girard and Jamie Sikora. And what we did is that we investigated some three types of compatibility of objects that we find in quantum theory. And so first, I'll just introduce these objects, and then I'll explain some of our results about these compatibilities and how they work together, and how can we use one to tell something about the other and stuff like that. And during all of the talk, please feel free to ask at any time, and just raise your hand or shout your question or whatever. So the first thing that we have is compatibility of states. So, I mean, small disclaimer, all of this talk is only about quantum theory. So no operational theories here, and if you were expecting that, but this is only about quantum theory. And so we have some finite dimensional Hilbert spaces, and we have quantum states, which are density matrices on the Hilbert space. And now we define the problem of compatibility of states, which is basically the quantum marginal problem, as follows. We take two states, but such that they have one Hilbert space overlapping and one different. So this X is the same everywhere, and these Y's are different. And we are asking about whether there is this bigger state rho on three Hilbert spaces, such that the ρ1 and ρ2 are the partial traces of this bigger state. So you can see it here on the picture. So we basically have here ρ1 as a state on two Hilbert spaces, ρ2 as a state on two Hilbert spaces, and we are looking for this big rho that would include everything. And so this problem is fairly common in quantum theory, and one can meet this at many different places. For example, one can use this to if we have something like ρ1 equal to ρ2, this is called symmetric extensions, and you can get a hierarchy for detecting entangled states from this. So a fairly common problem in quantum theory. So the second type of compatibility that we considered is a compatibility of POVMs, which is basically called also known as joint measurability. And the idea is as follows. A POVM is a set of positive operators that sum up all to the identity matrix, and this represents a measurement performed on the quantum system, and we get the probabilities by basically computing the trace of the state multiplied by the POVM element. And so if we take two POVMs, we say that they are compatible if there's a big POVM with two indices, such that you basically obtain the first two POVMs by summing over the indices. You can also see this in the picture. If the big POVM is here, represented by the rectangle, then if you sum along the columns, you get the second POVM. If you sum along the rows, you get the first POVM. So it's this notion of joint measurability is fairly known. It's somehow, if you consider that the POVMs are only projective measurements, then this simplifies to commutativity. So this generalizes like what we learned about commutative observables in Quantum 101. And this was also heavily investigated. And if you want to know more about this kind of stuff, I recommend almost any paper by Teiko Henosari, and you can find a lot of research done on this type of compatibility. And the third compatibility, and the one that will be most important to the talk, is compatibility of channels. So we already heard in the last talk something about channels. So we too define channels as CPTP maps, which means that they're completely positive and trace preserving. This completely positive just means that if you apply a channel to part of entangled state, you still get positive state. This trace preserving means that if you apply a channel to a state, you get the state with a trace equal to 1. And so now if we have two channels, we say that they're compatible if there is a big channel going from input state X to tensor product of output spaces, such that if we perform partial traces, we obtain the original channels. Now, in my opinion, the nicest thing to visualize this is using diagrams. And please note that in these diagrams, the time goes from left to right. So I think that's the two main things, like either from left to right or from bottom to top. So this is from left to right. And so this is the big channel phi. and it has one input. This is the Hilbert space X, this one, and it has two outputs. This is the Y1 and Y2. And here, this symbol is the partial trace. And so this first diagram directly corresponds to this equation, because it says that if we apply partial trace to the second leg of phi, we get phi1. And we apply, and this equality of diagram says that if we apply the partial trace to the first leg, we get phi2. So this is something you can already see that this is in structure quite similar to the quantum marginal problem, because we also have some partial traces. But on the other hand, one can also see that this somehow should have some connection to measurement compatibility or joint measurability, because in some sense, one can also encode measurements as channels, because if you perform a measurement, you can just say that you map your density matrix to a diagonal density matrix, and on the diagonal, we have the probabilities of observing the outcomes. So in some sense, channels live somewhere between, or channel compatibility seems to live somewhere between quantum marginal problem and joint measurability. And so this is directly connected to the first batch of results that we proved, because we proved two very important things. First one is that channel compatibility is equivalent to state compatibility. Now, let me unpack this. Going one way is very simple, because what you can do is that if you take the compatibility of channels as defined here, and then you can replace these channels by their Choi matrices, and you can scale those Choi matrices to obtain Choi states. And if you do all of this, you can see that this problem just becomes the quantum marginal problem for the Choi states. So clearly, any problem of compatibility of channels can be transformed into compatibility of the corresponding Choi matrices. What we proved is that you can also go the other way around. So if you start with a quantum marginal problem, you can do some fancy math tricks involving more Penrose inverse to obtain the problem of compatibility of channels. And this is essentially done also using the Choi-Yamiokovsky isomorphism, because what we showed that you can do is that you can always somehow normalize the states so that they become Choi states, and then the quantum marginal problem corresponds to compatibility of channels. But this result is quite important in light of the results that will be stated later, because this shows that now I can just prove stuff about compatibility of channels, and this applies to also quantum marginal problem, because you can always use this isomorphism to transport any results about compatibility of channels to compatibility of states. And this is actually very nice, because at least for me, I find it way easier to work with compatibility of channels than with compatibility of states, because you can also see channels as, you can use diagrams, and you can see channels as some things with inputs and outputs, and this makes it easier to think about all of that. The second result connects or shows the connection between compatibility of channels and joint measurability. And what we in principle show is that compatibility of POVMs and joint measurability is a weaker concept than compatibility of channels. This is because what one can do is that one can find some measure and prepare channels that such that the joint channel, the joint channel is this big channel phi, is not measure and prepare. So in some sense, compatibility of channels is more general than compatibility of POVMs, and one should not expect that any results that hold for measurements will also hold for channels, so weaker concept. So this is the first batch of results, and before we proceed further, I would like to ask if there's maybe some questions or anything.
Well, I think there are no, apparently there are no questions, so I think we can go further.
Okay, good. So let's go further. And now to the main topic of the talk, or the main results. And these are the Jordan products of POVMs. And actually, Jordan products of POVMs were known before, but why I'm going to tell you about this is because then I'll show you how to generalize this to Jordan product of channels. And so this is maybe a bit of a refresher, because people tend to know a lot about POVMs, and this is something very naive and something one can come up with very fast. And it's the following trick. If you have two POVMs, Mi and Nj, and let's say that you want to know if they are compatible. Well, I mean, you can you can write down the joint measurability problem. You can realize that this is an SDP. You can code the SDP and try to solve it on a computer. Or before you do all of this, you can try some very simple, very easy trick. And that easy trick is that you can basically try to guess the solution. And a very nice guess is given by this formula. So this thing on the left-hand side, we call this the Jordan product. And it's basically defined as the thing on the right-hand side. This has a very interesting property that if you sum here over J, what basically happens is that this POVM sums to identity, this sums to identity, here you get 2M, and so you get MI. If you sum over I, the same thing happens over here, and you get NJ. And so we say that this Jordan product has the correct marginals, because if you sum over if you sum over I or J, you get the thing that you want to get. But the problem is that this doesn't have to be positive semi-definite operator. But if all of them are positive semi-definite operators, then the two POVMs are compatible, and we just solved it almost with no effort. And there are some known results. For example, if one of the POVMs is a projection valued measure, which means that all of the operators are projectors, then basically they are compatible if and only if the Jordan product is positive semi-definite. Now, I would want to say that the Jordan product is not the best guess, but it is one of the guess that's worth trying, because if your POVMs are somehow reasonably noisy, it tends to often work, as we will also see later. Also, there is another thing that you can easily do, and that's that you can also take the Jordan product and you can compute the smallest eigenvalue of each of these operators, and you can use this smallest eigenvalue to basically estimate something like the lowest amount of noise you have to add to the POVMs to make them compatible. Because if you realize that this is a negative operator, you can always design some convex combination with some multiple of identity to make it positive semi-definite, and in this way you can get something like a lower bound on the noise that you have to add to make the POVMs compatible. And so in principle you get a lower bound, or you get some bound on the robustness of joint measurability, or robustness of incompatibility of measurements. And so now one of the main results, I'm going to show you how to do this for channels. And this is it. So what we do here is that we're going to rely heavily on the Choi isomorphism, and it's defined in such a way that the channel is applied to the second factor here. And this is not normalized to be a state, but if I say Choi state, I just mean the Choi operator normalized to a state. And so for two channels, we can define their Jordan product using the Choi isomorphism to be basically the linear map, the linear superoperator given by this Choi channel, by this Choi state, by this Choi matrix. And now the thing is that this Choi matrix doesn't have to be positive semi-definite. And so this channel, the Jordan product of the channels, doesn't have to be completely positive. But I mean, if it is, then the channels are compatible. And one can again easily check that this has the correct marginals, because if you trace over the second thing, here we get something like this is non-zero only if k is equal to j, so you get j here. If you trace here over the second thing, you must have I equal k, so you get I here, and so you basically get the Choi matrix of the first channel, and the same holds for the other one. Okay, so this is nice, because now we can, however this was constructed, this somehow generalizes the Jordan product of measurements. Moreover, if one would somehow consider measurements encoded as channels using that encoding, where you measure and put your probabilities on the diagonal, you can show that this would somehow reproduce the Jordan product of measurements. So this is nice and easy guess that you can always try if you want to do something about about compatibility of channels. But by the extent of the previous result, we can also apply this to the quantum marginal problem once we use the trick with the more Penrose inverse to transform quantum marginal problem into compatibility of channels. Okay, but now there is a natural question, like, is there more? Can we do more? And well, yeah, we can prove some more results, because I mean, the first thing that we can do is that we can take a channel defined as follows, which basically measures in a projection value measurement and puts the results on the diagonal. And then you can prove that this channel is compatible with any other channel if and only if the Jordan product is positive semi-definite matrix. So in some sense, this can be seen as a direct generalization of the known results for PVMs and POVMs and their Jordan product. But one can also prove similar results for unitary channels and for a constant channel, where the constant channel is a channel which just traces away input and outputs some fixed state. Although these two generalizations are less interesting because it's somehow trivial, because we know that unitary channels are compatible only with constant channels and constant channels are compatible with everything. Right. So one can recover the main results for Jordan product of POVMs. But we can go even further because we can also generalize the Jordan product. And actually, we can generalize it in such a way that it's not very easy to describe this generalization in full extent for POVMs, but I will give you at least a small clue of what it consists of. And the main idea is as follows. When we define the Jordan product of channels, we basically define it by one big equation, but one can see that this can be rewritten as follows. One can see that what we had here, so what we had 2 slides here, this thing, you can somehow play with it a little bit and you can see that it has this form, which is basically that we are applying something like identity channel and then the channel phi1 and then the channel phi2 on some big operator AJP, and this operator AJP is of this form, right? So you can easily see this is IJ, IK, KJ, and if you go back, this is the IJ, this is the IK, KJ, and the rest is all there. And now the interesting thing is that if we want to prove that this Jordan product has the correct marginals, it actually follows from this property, from a property of this operator AJP. Because you can see that if you trace here over, for example, over the second system, here we get something like I is equal to K, so you get I here, and here we get a similar thing. So you basically get this thing that we see in the inside Choi isomorphism, and it's essentially this and only this property that gives us that the Jordan product is correct marginals. And so now the obvious thing to do is to spin it the other way around, to basically stop using this fixed form of the operator IJP, but to just use this property. And this is what we call the generalized Jordan product. And what we show that you can do is that you can always take any operator on 3 copies of the same input Hilbert space, such that if you trace over the second and the third, you get this thing that we see inside Choi isomorphism. And you can define the generalized Jordan product as follows: that you basically apply the 2 channels to the fixed operator A. And again, we can get that the marginals are correct and the channels are compatible if and only if this is positive semi-definite. So we can generalize this guess and we can generate more and more and more Jordan products of channels. And one example that I find quite illustrative is to look at what this does to POVMs. And this is by no means the most general form that you can get for POVMs. This is just some very simple example, simplified as much as possible. And what we can do for POVMs is that we can take one operator such that its trace is equal to 0. And then we can define the generalized Jordan product of POVMs using this equation. And here what we basically have is that the generalized Jordan product is given as the original Jordan product plus this term. And the interesting thing about this term is that if you sum over I, you basically get here trace of y, and this trace y is equal to 0. And here we get the same if you would sum over j. So we basically can see that the sum over I of this is the same as the sum of the original Jordan product, which we know is nj. So we can perform this generalization and we can get way more easy guesses of these joint channels in the channel compatibility problem. And by the extent of the previous result, we can still apply all of this to the quantum marginal problem if we would need to. And so here are some more results, because we wanted to know about how efficient is this generalized Jordan product in actually constructing, in actually proving that two channels are compatible. And we basically proved two results, and they are mostly about channels which go from one Hilbert space to the same Hilbert space. So these are channels which go from Hilbert space X to Hilbert space X. So they don't change the dimension of the density matrices. And we proved that if such channels are invertible as linear maps. Well, this means that the channels are invertible, but the inverse does not have to be a positive channel. Because it is known that if you require that the inverse has to be positive, then the essentially set of such channels is very restricted. But here we say that the two channels must be invertible, but the inverse does not have to be positive. They just must be invertible as linear maps. Then they are compatible if and only if they're Jordan compatible, which basically means that they're compatible if and only if there is some operator A such that the generalized Jordan product given by A is positive semi-definite. And from this, you can easily get another result, which shows that the set of Jordan compatible pairs in channels that go from X to X, so they do not change the dimension of the system, has full measure as a subset of compatible pairs, which basically means that almost all channels are Jordan compatible. And so for almost all channels, there is some operator A such that the generalized Jordan product is positive semi-definite. Now there's a natural open question whether all compatible channels are Jordan compatible. So whether for all compatible channels there is some operator A for this, for which this is positive semi-definite, and this we don't know. So this is why we even proved this theorem, because it just says that if the set of Jordan compatible pairs has full measure, that means that we cannot randomly sample channels and try to hope to get something that's compatible but not Jordan compatible, because they have measure 0. So we don't know. This is still an open question. And from here, we also carried out some numerical experiments to see how well the Jordan product and the generalized Jordan product works. And so the first one considers this channel psi PQ, and we consider the self-compatibility of this channel with itself, which basically means that both phi 1 and phi 2 are equal to this channel. Because this is somehow, if you think about POVMs, then you can easily show that every POVM is compatible with itself, but this is not so much true for quantum channels. Not every channel is compatible with itself. For example, the problem of compatibility of identity channels with itself is basically the no broadcasting theorem. And we also know this from the quantum marginal problem, where we know that there's this symmetric extendability of state, which is basically asking whether the state is compatible with itself. So we call this the self-compatibility. And so what we can do with this channel is that we can find different regions of the parameters where different things happen. So at the top here, we have a region where this channel has a separable choice state. And so it is, one can easily show that it's self-compatible in here. And then there's this bottom curve where, which is like the boundary of the compatibility region. So down here, for these parameters down here, the channel is not compatible with itself, and up here, the channel is compatible with itself. And then there's this red curve, and this is the curve such that above the curve, the Jordan product of the channel with itself is positive semi-definite, and below the curve, the Jordan product of the channel with itself is not positive semi-definite. So we can somehow see that, and I would like to say that this is the first Jordan product that we defined. This is the naive one. This is not the generalized one. And so you can see that this actually includes a big chunk of the region of where the channel is actually compatible with itself, but it does not include the border region. So I would say that this shows that somehow Jordan product has a tendency to be a good way to prove that two channels are compatible as long as they're not very close to the border of the compatibility region. And then there's a second example. In this example, we actually consider different channels, and we consider these channels omega q, which are given as this. So it's a convex combination of identity and a constant channel. And it is known that inside this region, above the black curve, the channel omega q0 is compatible with omega q1. So here the channels are different. And here one can show that the Jordan product, the first one, the simple one, gives a region which includes a huge part of the compatibility region, but again, it's somehow there are these cases where the channels are compatible, but this is not proved by the standard Jordan product. So again, one can use the Jordan product to construct the compatible channel in some simple cases, but we can see that close to the boundary of the compatibility region, this is not so optimal anymore. And with this, I would like to thank you for your attention. And if there are any questions, please feel free to ask.
Yeah, thanks a lot, Martin. So surprisingly, we have a lot of time for questions. So let me maybe first ask a question, because so you have this Jordan decomposition given by A. Do you know how many, let's say, independent choices of this A you can have? Because apparently one could think that perhaps there are many choices which at the end they give the same, because you rotate something and the result is more or less the same.
Yes, that's a good comment. So actually, one can show that out of these A's that satisfy this condition, this is something like a affine subspace. So that's a lot. That's a lot, and it's also like unbounded set, so we cannot do limits over the set. But we don't know if you can reduce this to something like a smaller set. This is so far unknown.
Okay, so I'm asking more or less whether perhaps it can be that you have two different A's, but at the end they give the same result, but you need to rotate your POVM, for instance, by like locally, whatever. The question is whether nothing yes, like that happens.
Yes, this can definitely happen, and I think that one can easily handcraft a scenario where this happens, but well, this depends. This is usually the case if you change the dimension of your system using the channel, because then you can just somehow you get some more freedom, you know. So okay, it can happen that for two channels, different A's produce the same generalized Jordan product. But then I would say that maybe if you are allowed to vary the channels as you wish, then you can always somehow detect the difference between the A's. But well, this is a good question for follow-up research, I would say.
Okay, thanks a lot. So we have